let us go ahead and start again, like I said, with systems of equations using Cramer's rule. So let's say we have a problem like, let's see, x minus 3y equals negative 2. Is that right? No. Let's make it negative 5. And then 2x plus 4y equals 10. Okay? So let's say this is, in our analysis, we wind up with these two equations with two unknowns. And maybe this is the reaction forces at a certain support. So our bridge is supported at a certain location by a column. And I want to know, what are all the forces on that column? Well, there's going to be some forces in the x direction and some forces in the y direction. And that's what these variables represent. And so I already know, if I want to do this by basic algebra, I would do substitution method. I would take one equation, solve it for one of the unknowns, let's say x in the first equation, and then I'd substitute that x into the second equation. Now I'll have a big long equation with just y in it. Solve that for y. I now have an answer for y. Take that answer for y, plug it back into the first equation to solve for x. Perfectly fine, legitimate thing to do. However, for our purposes, we're going to learn this new technique, or at least review it, and that is to use matrices, and in fact the determinant of matrices, to be able to solve the same problem. And so what are the steps to being able to do this? Well, first thing you have to know is, how many matrices do you have to set up ahead of time? So I have two equations with two unknowns. That means I need one more matrix than the number of equations, or than the number of unknowns. So I have two equations, I need three matrices. So what are the three? The three matrices, or the matrices you always use depending on the number of equations, is one matrix for each variable. So I have an x variable, so I'll have an x matrix. A y variable, so I'll have a y matrix. And then keep going for as many variables as there are in your problem. And then at the end, one extra matrix, and that is always called the W matrix, which again stands for Vronsky. And this matrix is special in some way. So three matrices because we have two variables in our problem. How do we set up the matrices? We'll start with the W matrix first. That's the easiest. The W matrix is going to have elements which are nothing more than the coefficients in front of your variables in your equations. So the left column, which are the numbers, the elements that go with the x variable, I've got 1 and 2. Okay. And in the second column are the elements that go with the y variable. And in this case, I have minus 3 and 4. And that's always how you set up your W matrix. You look at your equations, take all the coefficients in front of all the variables, and you set up a matrix using those elements. Now the other two, or the other ones, the ones that have to do with the variables themselves. It's very similar. You're basically going to copy the Vronsky, except for making one correction to it. And a correction goes like this. If you're looking at the matrix for the x variable, then all the elements that have to do with the x column, you're going to change them to be the answers to your equations. All the other elements stay the same as the W. So in this case, there's the x stuff and the y stuff. If I'm looking at the x matrix, the y stuff stays the same as the W. So I could just write those in now. Negative 3 and 4. Those don't change. But since I'm looking at the X matrix, the X elements, the left column, I don't put the coefficients from my equations. Instead, I write whatever the answers are to my equations. And so that is -5 and 10. Okay. And then the Y, the other one, same exact process. This matrix is going to be just like the W, except since I'm looking at the Y matrix, the Y variables change. So my X stays the same, 1 and 2. But now instead of writing the Y coefficients, I write the answers. So that's -5 and 10. And again, if you have a system of equations with more than 2 equations, maybe let's say we have 4 equations with 4 unknowns, then I'm going to set up 5 matrices, 1 for each variable plus the W. The W will be a matrix with elements that are purely just the coefficients in front of all the variables. And then for each one of the variable matrices, take the X one first. I just rewrite the W matrix, except for the X column, I write the answers to my equations instead of the X coefficients. For the Y, it's the same as the W, except the Y column is now the answers, and so on for as many as we have. All right, so there we go. I've set up my problem. I now have all the information I need to be able to go ahead and do the process. I've come up with my matrices. Now what do I do? Cramer's rule says if you want the answer, the value for X, your first variable, let's say, then all you have to do is take the determinant of your X matrix and you divide that by the determinant of the W matrix. Okay? And if I do this process, whatever the heck that means, if I get an answer, that must be the answer to X. Now, note, this is very important because what it shows is all the information about Y, I don't have to go find the value of Y before I can get X. I can get X directly without looking at Y at all. Whereas in the regular algebra case, you do have to worry about Y first before you get X. And if you want Y, you have to get X first before you get Y. So let's see. What did it mean to take a determinant? We saw last time that a determinant depends on how big your matrix is. If your matrix is a 2 by 2, then it's fairly easy. For a 2 by 2 matrix, I'll do it right here just to remember. You have A, B, C, and D. The determinant, the way you write it, is instead of these kind of parentheses, you do absolute values. So that makes it determinant. And the determinant becomes kind of, the way I think about it is cross multiply and subtract. So A times D, so I'm going down the diagonal, A times D, A times D, and I'm going to subtract the other diagonal, B times C. And you do this process, that gives you the value of the determinant for this matrix. And so the 2 by 2 matrix, very easy process to do. You can do it very quickly. As your matrices get bigger and bigger, this process gets more and more complex. It's more tedious, really. It just takes more steps to do. And we saw last time how to do a 3 by 3. But for now, let's just concentrate on the 2 by 2. So I want to do the determinant of the X matrix. Well, let's look at the X matrix here. I've got -5 times 4, so -5 times 4 minus, that's -3 times 10. So that's the determinant on top. Main diagonal, -5 times 4, minus the other diagonal, -3 times 10. And we do the same thing for the W matrix on the bottom. Well, we've got 1 times 4, 1 times 4, minus negative 3 times 2. And there we go. Now all I have to do is simplify this down, get the numbers, and I'll have my answer. So what does this become? Negative 5 times 4 is negative 20. And minus negative 3 times 10 is plus 30. All divided by 1 times 4 is 4. Minus negative 3 times 2 is plus 6. So I've got 10 on top, 10 on bottom, which gives me 1 as the value of x. So I now have one of my answers. Perfect. Let's say I need to know y. Same basic process. If I want to know the value of y, I take the determinant of the y matrix over the determinant of the w. So let's do that really quickly. Looking at the y matrix, we've got 1 times 10 minus negative 5 times 2. And in the good news, the W matrix, we've already done it. We already know the value of the W matrix determinant is 10, so we just stick 10 down there. We don't have to go through the calculation a second time. So what do we get? 10 plus 10 over 10, which is 20 over 10, which gives me 2. Okay. It looks like we can go ahead and check our answer just to make sure this works. What we want to do to check is take your value of x and your value of y and stick it into your original equation. See if they work. So x was 1 minus 3 times y was 2. And what do we get? 1 minus 6, which of course is negative 5. So that one works. And of course you can do the same for the bottom one, and that works as well. So it checks out. That's Cramer's rule. It's a new way, a new technique of solving linear systems of equations or simultaneous equations. And it's very helpful. It's especially helpful as you get to more realistic problems, as I said last time. In real-world problems, you won't have just 2 equations or 3 equations. You may have 10,000 equations. And certainly, you don't want to sit there with a piece of loose leaf trying to solve 10,000 equations with 10,000 unknowns. What you're going to do is get on a computer and tell the computer to solve it for you. Well, the computer, when you give a computer a problem to do, you want it to take as little time as possible because you don't feel like sitting there. You type up your little program, have it run, and you don't want it to run for 5 hours trying to calculate everything. You want it to take a second to calculate everything. Well, if you try to make the computer do it the regular algebra way, that takes way longer because you're not just solving 10,000 problems. You're solving 10,000 problems just to go the first way down, and you got to go 10,000 more the other way. Here, if you know this technique, this is more natural for a computer to do. A computer likes working with matrices and vectors and things. So you would feed the computer the problem in matrix form, and it can solve these problems way more efficiently and way more quickly this way. So this is a good technique to know. In this course, as I said last time, I will not force you to use one technique over the other in general. I may want to test to see if you know it, in which case I'd be specific about it. But for a normal problem, where this is just part of solving the problem, you can use any technique you want as long as it's a legal math technique. Okay, so don't worry about, oh, I'm kind of confused about this method, I'd rather just use algebra. That's fine for this course. Are there any questions about using Cramer's rule? All right, let me go ahead and show you, just as a review, really quick, if you have a 3 by 3 matrix, how do you solve it? So let's have our general 3 by 3 matrix sitting here. And I want to do the determinant of this 3 by 3 matrix. We saw how to do the 2 by 2. Now let's do the 3 by 3. What I'm going to do is go ahead and write this 3 times so I don't have to erase. All right. So I just rewrote it 3 times, but how do we do it? First thing you do is you start on the top left, the very first element. So we start on A. So we write A times. Then we cross out any element that's in the same row as A and the same column. So A goes away, B goes away, and C goes away. That's A's row. A's column gets rid of D and G. And now you see you're left with this little 2 by 2 set of elements on the bottom right. And now we just treat it like a 2 by 2 matrix. So we have E times I minus F times H. So that piece is done. Next, you subtract automatically, minus. Now, let's look at the second matrix that I wrote, the second copy, because it's clean, it doesn't have the lines on it. Now what I'm going to do is move to B. So I now have B times, and do the same thing. Get rid of B's row and get rid of B's column. And now we see, again, I've got 4 elements, kind of like a 2 by 2 pattern there. And so I say D times I minus F times G. And now that piece is done. Then you say plus, automatically plus. So the first term is positive, second term is negative, third term is positive. Of course, A, B, and C can also be positive or negative, so be careful about the signs. But just in general, it's the A minus the B plus the C. So now we're moving to C, so I look at the C element, run C, and then I get rid of C's row and C's column. And again, we get this little 2 by 2 thing, so we say DH minus EG. And that's how we do our 3 by 3 matrix. Of course, these would all be numbers. Simplify it down, you'll get an answer, a number for this thing. But it's taking the 2 by 2 matrix rule and having to do it 3 times. And each time you do it, you're multiplying by one of the elements of the first row. Now, this is very important to know how to do, because we're going to see this thing crop up again in a different operation. So this is doing determinants. We're going to see us having to do this determinant thing on a 3 by 3 matrix when we get to what's called cross products, which we'll talk about when we get to vectors. So knowing how to do this is important, not just for Cramer's rule. So don't think, oh, I'm not going to use Cramer's rule so I don't have to remember this. You do have to remember this. Or not remember, but you do have to know how to do it. I don't memorize these letters, ever. I just do the operation. But later on, we'll see we'll still have to do this operation even if you don't use Cramer's rule. So don't throw it away. All right, now with that, I do want to get to vectors. We've seen vectors in general physics, so we're all used to these vector things. Vector, of course, is the one higher dimensional version of a scalar. A scalar is a number, 25, 71, whatever. A vector is this abstract idea, this object, which contains two pieces of information. Generally speaking, it contains the magnitude, so how fast, how far, how hard, whatever, and a direction. So speed is a scalar, 35 miles per hour. Velocity is a vector, 35 miles per hour east, that kind of a thing. Vectors are important in this course because every problem we do will be a vector problem. Every one. In general physics, some problems didn't use vectors, like energy doesn't use vectors. But here we will be using vectors. And the reason I want to go over it is because engineers have a different language and a different way of doing things with vectors, and you need to see that. You can't just rely on your knowledge from physics, even if you know it very well from physics, you have to see what the engineers do and how they write things slightly differently. So let's start off with a vector. Let's say we have a vector which is vector v is 10 meters at 30 degrees north of east. Okay. So there's our vector. What does it look like if I were to draw it? Well, here's east. I'm going 30 degrees north of east, so it'll be a little arrow that comes out 10 meters and whose angle is 30 degrees sitting there. Yeah, that's our vector. What do we want to do with the vector? Generally speaking, if you're given a vector, the first thing you want to do is get its x and y components. Because probably what's going to happen is we're going to have a problem where we have to add a bunch of vectors together to get a solution. And the only way to add vectors together is if they're in the same direction. And the likelihood of that happening is fairly zero. So we get around it by calculating x and y components of all of our vectors. And then we could add up all the x stuff because they're in the same direction, and add up all the y stuff because they're in the same direction. And then we do some math at the end to collect all that information into one vector again. So let's try it. We remember, given a vector, if we want to find the components, we pretend like there's a little right triangle sitting here, the x side and the y side, and we use SOHCAHTOA to help us figure out what to do. So in this case, if I want the x component of v, I take the magnitude, which is 10, and I'm either going to use cosine or sine. In this case, I want to use cosine because the side I'm looking for is the x side, and that side, relative to the angle, is adjacent. If you look at the little right triangle on the right, the angle sitting there, the x side is the adjacent side, the y side is the opposite side. So I'm going to use cosine because cosine goes with adjacent. So it's cosine of 30. Okay. So I get 8.66. And then if I want the y component, I take the magnitude, 10. And now I'm looking for the y side. That's opposite. Opposite goes with sine, so it's 10 sine 30, which gives me 5. So now I have my components. Now here's what you need to know. Mathematicians, physicists, and engineers write things differently. They all mean the same thing, but we all have our little quirks about how we want to define things. Well, physicists and mathematicians are pretty close. They pretty much agree on how to write things in general. And if I wanted to write down this vector, and I don't want to write it in this magnitude and direction form, the other way I could write the vector is by saying the vector v is some amount in the x direction and some amount in the y direction. And so to write it, I'd say, okay, take the x component, 8.66. Now I have to have some way of letting the person who's reading this know that it's this amount in the x direction. But I don't want to say x because usually when I'm doing this stuff, I'm doing it on equations, and these equations probably have x and y as variables. So I don't want to say 8.66 x direction, but I still need the person to know it's the x direction. So they came up with a symbol called I with a little hat on top. I hat. I hat. And that is defined to be the unit vector in the x direction. So it's a little vector with magnitude 1, so it's unit length, unit magnitude, and all it does is give a direction to this number 8.66. It says it's a magnitude of 8.66 in the direction called I hat, which is the x direction. Then, plus, how much in the y? The y component, which is 5. And now again, I need to give a symbol that says this 5 is in a certain direction called the y direction. And I use the letter J, J hat. So J hat is the same except y direction. And so that's how a physicist or a mathematician would write the vector v. 8.66 I hat plus 5 j hat. And that means the same as the vector I wrote up here. There's just two different ways of writing it. The good thing about the bottom way of writing it is it's very, very useful for someone who's about to do some work with the vector. If I'm about to have to add a bunch of vectors together, I don't want to have to find all the x and y components. If you can give me the x and y components automatically, it makes the problem a lot easier. So, two different ways of writing a vector. One tells me the magnitude and direction. The other tells me the x component and the y component. They both give me exactly the same amount of information. Two pieces. They talk about how long and in what direction, but they do it in different ways. Now this is useful for normal vector algebra because, like I said, if I want to add two vectors together, let's say I have vector A is A, let's not use A, let's use, let's say C in the I hat direction plus D in the J hat direction. And then I've got B, which is in the E in the I hat direction, and F in the J hat direction. So those are my two vectors. I want to add these two vectors together. How would I do it? Well, if you remember, in general physics, you're given two vectors, find the x and y components of the first, find the x and y components of the second, add the x's, add the y's. Well, here, we already have the components written out for us. Everything in front of the I hat is the x component, everything in front of the j hat is the y component. So if I want to add A plus B, what I have to do is I say the AX plus the BX in the I hat direction, and the AY plus the BY in the J hat direction. Right? The x component of A plus the x component of B is the total amount in the x direction, and the y component of A plus the y component of B is the total amount in the y direction. So for us, this would be C plus E, I hat, plus D plus F, J hat. And we'd have our answer. The problem giver gave us vectors in x and y components automatically, so I just add the components. Very nice. Makes problems a lot faster if you have it in this format. Now, what's different between what a physicist would do and what an engineer would do? Well, an engineer likes this, except for whatever reason, they tend to be more lazy. And so they want to write less than what a physicist writes. And so what an engineer would do is take the same principle of A as a vector is C I hat plus D J hat, but they will write it parentheses to let everybody know this is about to be a vector, C comma J. No, not J. What am I thinking? C comma D. And that's how they would write it. And it's telling you the same thing. They're basically saying the first element is the x component, the second element is the y component. It's just that if you don't know from context what this is trying to tell you, this is not a point necessarily on a graph. This means a vector. And the vector whose x component is C and whose y component is D. So it just lets them write things down a little quicker. And sometimes you'll see it without even the commas. Sometimes you'll also see it just as C and D with a space in between, just so they write it quicker. So that's what an engineer would write. But note, it means the same thing as what a physicist would write. It's just the physicist expresses the directionality with these I hat, J hat. If you have a three-dimensional problem, K hat is the Z direction. Now, we need to know more than just adding vectors. Adding vectors is easy. A plus B is the x component of A plus the x component of B, blah, blah, blah. There are other things we may have to do to vectors. For instance, multiply vectors. We may need to multiply at some point. And so we need to know, how do we do A times B, given that A and B are vectors? Well, if you recall from general physics, this is a complicated problem because there's not just one way to multiply. There's many ways to multiply. The two we're going to discuss are what's called the dot product and the cross product. Two different types of multiplication. The way they're written, dot product is A vector dot B vector. Cross product is A vector x B vector, or cross. They say cross, but you write it like a little x. And these two things are completely different. They're both multiplying two vectors together, but the way you multiply is different, the answer you get is different, and the meaning, the physical interpretation is different. For instance, with a dot product, you start with two vectors, A and B. You do this type of multiplication, and the answer you get is not a vector anymore. You get some scalar, C, a number. It's not a vector. It has no direction anymore. Whereas with a cross product, if you do the vector A crossed with the vector B, you get some new vector C. So dot product, some kind of multiplication that gives you a number. Cross product, some kind of multiplication gives you a vector. Also, physical interpretation-wise, because obviously, unless you're a mathematician, when you look at these, you want to know, what do they represent? What are they trying to tell you about the system? A dot B, a dot product, is kind of like asking how much of B is in the direction of A. So if you have two vectors, here's two vectors, here's one and here's two, A and B, and you want to know, okay, what is the component of B that's in the A direction? How much of B is in A's direction. Okay? That's generally true. What we usually use it for is, here's A, and here's the X direction. I want to know how much of A is in the direction of X, right? That's finding the X component. Well, at the heart of finding the X component, you're actually using the dot product. You just don't realize it. Because you have the X direction is a vector that points in the X direction. A is a vector that points in some other direction. And I want to know how much of A is in the same direction as X. That's what a dot product gives you. But if you have two vectors that are just general, not the X direction or the Y direction, you can do the same exact problem. How much of A is in the direction of B? And that's what a dot product tells you. So it gives you a magnitude. 2 meters of A is in B's direction. So there's no directionality to it. It's just a number. Cross product is different. Cross product kind of tells you about how perpendicular two vectors are. Or another way of saying it is, if you multiply A and B, two general vectors, then it tells you how perpendicular they are, and it gives you a new vector that points in a direction which is perpendicular. So A dot B is how parallel they are, how much of A is in the same direction. A cross B is like how perpendicular, how much of A is away from B. And it gives you a new vector which points perpendicular to both A and B. So what you see in math courses, if you see this thing in math, what they usually use it for is to say, is vector A perpendicular to vector B? And so you would, or is vector A parallel to vector B? If they're parallel, then if you do a cross product, you'll get 0. And if they're not, then you'll get some new vector. So these are the two kinds of multiplication. We're running out of time, so I'll go ahead in the next lecture. I'll go ahead and show how to do dot products and cross products, especially with this new way of writing down a vector, this new notation, I should say. Given this notation, these two operations are now a lot easier to do. And we'll see that in the next lecture.